Welcome back to KSET previous year question and solution classes. Today I will discuss classical mechanics 2015 paper, and this is from paper 2. Okay, so the question is like this: if the force acting on a particle are conservative, then which of the following quantities is conserved? Total energy, linear momentum, angular momentum, both linear and angular momentum. Answer is total energy. Why? Because see, we know that total energy is nothing but changing energy or final energy minus initial energy, or difference between initial energy and final energy. So which is nothing but work done. So therefore work done is nothing but total energy, so which is also equal to force into displacement, integration force into displacement. So let us consider this is the particle. If the force acting on this particle, it takes displacement. So this force into displacement is nothing but work done, which is also equal to total energy. So therefore total energy is conservative. So option A is correct. Next, the question number 10. For circular and parabolic orbits in an attractive 1/r potential having the same angular momentum, perihelion distance of parabola is. Options is like this: double the radius of circle, equal to the radius of circle, half the radius of circle, and thrice the radius of circle. Answer is half the radius of circle. Why? Because see, perihelion means point where the planet is nearer to sun. So that point is called perihelion. And aphelion means the point where the furthest or the longest distance of the sun is called, that means the large distance between the planet and sun is called aphelion, and the shortest distance between the planet and sun is called perihelion. Okay, so the equations which are describing the orbits are r is equal to L square divided by mk for circle, and r is equal to L square divided by mk into 1 divided by 1 plus cos theta for parabola. Okay, next, the perihelion of parabola occurs only when theta is equal to 0 in equation 2. Therefore r is equal to L square divided by mk into 1 divided by 1 plus cos 0, which is equal to L square divided by mk into 1 divided by 1 plus 1. So which is equal to L square divided by mk into 1 by 2. So which is equal to L square by 2 mk. This L square mk is nothing but r. So therefore r prime is equal to r by 2. So which indicates by radius by 2. So half of the radius of circle. So this is the radius of circle, and 1 by 2 the times the radius of the circle is the perihelion distance of parabola. So option C is correct. So this is the question number 11. Lagrangian for a compound pendulum is of L theta dot square minus mgl cos theta, sorry, this is I, of I theta dot square minus mgl cos theta and of I theta dot square plus mgl cos theta and m r dot square plus r square theta dot square plus of L theta dot square minus mgl cos theta, and this is another option. So let's see the Lagrangian of a compound pendulum. So what is compound pendulum? So a rigid body capable of oscillating in a vertical plane about a fixed horizontal axis is called compound pendulum. So let us consider this is a reference axis, okay, where the potential is 0 here, and below the potential is negative and above the potential is positive, okay. So therefore here from this point, so let us consider this is our compound pendulum, okay, so which is fixed and it has free to move like this. So it is moving, it is oscillating like this, okay. So at a fraction of time, so it is moved from a distance, so here to here, so which makes some angle theta, okay. If I draw the perpendicular, suppose this is O, this is P and this is P prime, it looks like a triangle which makes 90 degree, and this is O, P, this is the length L of the pendulum, the length of the pendulum, okay. So next, so we know that Lagrangian L is equal to kinetic energy minus potential energy. So what is kinetic energy? Kinetic energy is equal to of, for a rigid body kinetic energy is of I omega square, and potential energy V is equal to the general expression is mgh. Here height we have to calculate, okay. We know that so this is the height and this length L. If so here, so let us consider a pendulum is just as a moved from, it is moved from the center position to a small displacement which makes an angle theta, okay. If you have to take a resolution of this point along the normal direction, so that is cos theta is equal to adjacent is nothing but OP by hypotenuse is L, so OP is equal to cos theta into L. So this OP is length or height, so therefore V is equal to mg L cos theta. Therefore if this is equation number 1, equation 1 becomes L is equal to of I omega square minus, so potential energy, so this is below the reference axis, that means we can assume it as a negative y axis, so the potential is negative in terms of negative minus mgl. So because the pendulum is moving upward direction but gravitation is towards the ground, so we can also think like that, so that's why you can think as a negative sign. So negative into negative of mgl cos theta, and which is equal to of I omega square minus into minus plus mgl cos theta. So from the option C, A, B, C, D, from these options, option B is correct, right? So option B is correct, I theta dot square plus mgl cos theta. Next, question number 12. Hamilton's canonical equation of motion R. So option B is correct. So that is Qi dot is equal to dou H by dou Pi, and Pi dot is equal to minus of dou H by dou Qi. That means if suppose this is theta dot, which is equal to dou H by dou P theta, and P theta dot is equal to dou minus of dou H by dou Q theta. So like that. If suppose this is R dot, so then this is PR. If this is PR dot, so then it is QR. So like that, coordinate and momentum. So if momentum have dot, so it is minus, and coordinate as dot, it doesn't have minus. So option B is correct. Option B is correct. Next question is question number 13. When the body is constrained so as to rotate only about a fixed axis, then moment of inertia is 0, variable, constant and non-zero. So when the body is constrained so as to rotate only about a fixed axis, is a constant moment of inertia. Okay, so the body is fixed in a particular point. So like this. So if suppose this is the reference axis, so here there is a point. From this point, for example, let us consider a rigid body, so which is fixed. When it is fixed, if suppose let us consider here there is a mass and the distance is r, so then moment of inertia, we know that I is equal to mr square, and this is constant. While rotating, their mr square is not changing. So answer is constant. Next question is, the rest mass of an electron is m naught. When it moves with a velocity of 0.6 c, then its mass is m naught, 5 by 4 m naught, 4 by 5 m naught and 2 m naught. So the rest mass of an electron is m naught. So this electron moves with a velocity of 0.6 c, that means approximately equal to velocity of light. So then let's see, the answer will be, so we know that when the particle moves with a velocity of light, then its mass correction is gamma m naught, Lorentz correction gamma. So what is gamma? Gamma is equal to 1 by square root of 1 minus v square by c square. So which is equal to 1 divided by square root of 1 minus, what is v? 0.6 c divided by c. Okay, so which whole square? Then this c and this c cancel. So remaining is 1 divided by square root of 1 minus 0.6 whole square. We can write this for simplification, which is equal to 1 minus, so this is 6 and this is 10, and which is whole square. So then which is 1 divided by square root of 100 minus 6 6 are 36 divided by 100, which is equal to 1 by root of 6, so 64 divided by 100, right? Next, if we take 64 from the root, it will becomes 4, and if you take 100, it will becomes 10, so which is equal to 10 by 8, and 8 to 4s are to 5s are, so 5 by 4 is the answer. So 5 by 4 m naught, option B is correct. Next question is 15th one. A cylinder rolling without slipping down a rough inclined plane of angle theta is an example of scleronomic, holonomic, conservative system only, and scleronomic conservative system only, conservative system only, scleronomic system only. So the question is like this. Let us consider an inclined plane. A cylindrical body is, so this is rolling, but it is not slipping. So it has linear motion and as well as angular motion. So therefore we can possible to write in terms of an equation. If it is possible to write in terms of an equation, then it is holonomic. And scleronomic means, or we can also call it as scleronomic. That means so which is independent of time, and this is also independent of time. So the total energy of these rolling bodies does not depend on time. So therefore it has holonomic and as well as scleronomic. So option B is correct. So this is option B. Next question from part 3 of 2015. A classical particle is moving in an external potential field V of x comma y comma z. Identify the conservative quantity and the symmetry operation. So x comma y comma tends to x z y z, and which is equal to r z of x y, where r z denotes the 2 cross 2 matrix corresponding to rotation about the z axis. So this is x axis, and let us consider this is y axis, and initially it is like this. Okay. So if the body is slightly rotating about a z axis, so our new x prime is this one, and our new y prime is this one, which makes some angle theta with x axis, which makes some angle theta with this y and y dash. So then after solving this, we will get some matrix, so that includes rz. So then which of the following is conservative? X and y components of a linear momentum, z component of an angular momentum, z component of angular momentum and energy. So z component of linear momentum and z component of angular momentum. So actually z component of angular momentum, because it is rotating. So z component of angular momentum and energy is conservative. So option B is correct. The autonomous Hamiltonian systems are fields that the fixed points are. So what is autonomous? Autonomous means it's a time independent Hamiltonian. That means Hamiltonian does not depend on time. So in this autonomous Hamiltonian, systems are fields that the fixed points are. So stable and unstable, spirals, elliptical and saddle, stable nodes, unstable nodes. So answer is elliptical and saddle. So the Hamiltonian is preserved, this volume is preserved in classical mechanics. So it has fixed points. The fixed points for this Hamiltonian in classical mechanics are parabolic, okay, or shear point, next elliptical or center, next another one is saddle point, is nothing but hyperbola. So what is the saddle point? It looks like this. Okay, so option B is correct. Next question is, if the coordinate q and the corresponding canonical conjugate momentum p undergo a linear transformation, so then q is equal to alpha q. So this is alpha q plus beta p, and p is equal to gamma q plus delta p. So the transformation is canonical if. So for canonical transformation, we know that the conditions is dou q by dou small q and dou q by dou small p and dou capital P by dou p and dou capital P q and dou capital P by dou small p is their determinant value is to be equal to 1. So let's verify this. Differentiate q with respect to small q, which gives alpha, right? Alpha. Differentiate this q with respect to small p, so which gives beta, and differentiate the small capital P with respect to q, small q, which gives gamma, and which gives delta if you differentiate with respect to p. Let us take a determinant of this. So alpha into delta minus gamma into beta, so which is equal to 1. So answer C is correct. In the Hamiltonian-Jacobi theory, canonical transformation q comma p to capital Q comma p is solved such that the new canonical pair q comma p satisfy the dynamic equation. So here in Hamiltonian-Jacobi theory says that when q is changes to new coordinate q and their moment has to be conservative if h does not depend on time. If in case Hamiltonian involves the time, then this method is not applicable. So then the new Hamiltonian h prime is equal to 0. Actually that h prime is nothing but h plus dou f by dou t, and therefore the canonical transformation from the old set variables, the canonical transformation from old set variables q k, so q p, small q small p to capital Q capital P is capital P dot is equal to minus dou h prime by dou q and capital Qk dot is equal to dou h prime by dou p. Okay, so this is, but h prime is equal to 0, then this pk is equal to this p dot is also constant and q dot is also constant. So then p dot is equal to 0 and q dot is equal to 0. So therefore option C is correct. The Lagrangian of a simple pendulum is given by L is equal to half ml square theta dot square minus mgl of 1 minus cos theta. The Poisson bracket between theta and theta prime is given by C. Lagrangian is this one, right? And we know that p theta is equal to dou L by dou theta dot, which is equal to, differentiate this Lagrangian with respect to theta dot, so then we will get ml square theta dot. Therefore theta dot is equal to p theta divided by ml square. So the Poisson bracket of theta comma theta dot gives, so let us write theta comma p theta divided by ml square, but theta comma p theta into 1 by ml square. We know that theta comma p theta is equal to 1, so therefore answer is ml square. So option A is correct. So anyone r comma pr is equal to 1, x comma px is equal to 1. So option A is correct. Question number 14. The function f of qi comma pi is equal to qi pi, where qi are the old generalized coordinates and pi are new generalized momenta, generates the transformation. So we know that present missing is equal to dou f by dou present. So here what is missing here in terms in qi pi, if I take a qi, their corresponding small pi is missing, which is equal to dou f by differentiate with respect to small qi. So answer is p dou f, this is the function f, differentiate with respect to qi, you will get capital Pi, and with respect to capital Pi, capital Qi is missing and dou f by dou capital Pi. So then which is equal to, if we differentiate with respect to capital Pi, so then we will get small qi. So for capital Q you will get small q, for small p you will get capital P. So answer is q to q, q to q, p to p. So option A is correct.